In the second lecture over valence bond theory, we'll describe the types of orbitals that can form sigma and pi bonds. Let's begin. The overlap resulting in the single bond shown here occurs along the internuclear axis, forming a sigma bond. Sigma bonds refer to the head-to-head overlap of any type of orbital as long as the overlap occurs along the internuclear axis. So just imagine this overlap as if it were two trains meeting on the same track, where the track is the x-axis. Let's look at each of these examples. We have molecular hydrogen, where two s orbitals overlap, hydrogen chloride, with overlap between an s and a p orbital, molecular chlorine, with the head-to-head overlap of two p orbitals, methane, CH4, with the overlap of s orbitals in each of the sp3 hybridized orbitals, and ethane, CH3CH3, with two types of sigma bonds being formed, one from the overlap between s orbitals and sp3 hybridized orbitals, and the other from the overlap between two sp3 hybridized orbitals along the x-axis. While it's not incredibly relevant now, in later chemistry courses, it will be important to know that the rotation of atoms around a sigma bond does not interfere with the head-to-head overlap that forms the bond. This means that molecules like ethane have a greater number of ways that they can exist in three-dimensional space, rather than being locked into a single position. Here's a question for you. If sigma bonding covers single bond formation, how do we get double and triple bonds? Let's take a look. In the last lecture, we examined the sp2 hybridization that formed the three electron domains around each carbon in ethene, C2H4. Now let's look at how the bonds are formed. As the two carbons in ethene approach each other, a sigma bond forms from the head-to-head overlap of the sp2 hybridized orbitals along the x-axis. At the same time, the unhybridized p atomic orbitals become close enough to overlap. This forms a second bond with both lobes of the p orbitals overlapping side to side. The second bond exists in two separate areas of overlap, above and below the internuclear axis, and is designated as a pi bond. Double bonds, then, are made up of one sigma bond and one pi bond according to valence bond theory. Let's take a quick look at the animated process to see how it works. In the last lecture, we also examined the sp hybridization that formed the two electron domains around each carbon in ethine C2H2. Now let's consider how the triple bond is formed. As the two carbons in ethine approach each other, the overlap between sp hybrid orbitals forms a sigma bond along the x-axis. At the same time, the unhybridized p orbitals become close enough to overlap and form pi bonds. Since there are two sets of unhybridized p orbitals, the overlap forms two pi bonds, one in the xy plane and the other in the xz plane. Triple bonds, therefore, as shown here for ethine, are made up of one sigma bond and two pi bonds. Let's take a quick look at the animation of this process. Let's work through an example together. If we look at the central carbon atom, we see it has three electron domains around it, none of which are lone pairs. This gives us a trigonal planar electronic geometry. Carbon forms three sp2 hybrid orbitals. Carbon forms two sigma bonds by overlap between two of its hybrid orbitals and the 1s orbitals of two hydrogen atoms. Carbon forms a third sigma bond by overlap between an sp2 hybrid orbital and a p orbital on the oxygen atom. The unhybridized p orbital on carbon overlaps with a p orbital on oxygen to form a pi bond. Here's one for you to try. How many sigma and pi bonds can you count in this structure for acetylsalicylic acid? Keep in mind that each double bond contains both a sigma and a pi bond. Here's the answer. All 16 single bonds are sigma bonds. The 5 double bonds contain 1 sigma bond and 1 pi bond each for a total of 21 sigma bonds and 5 pi bonds. In this lecture, we've considered how to hybridize atomic orbitals to make up to 4 electron domains around a central atom, which gives us a tetrahedral electron geometry. So how do we get 5 and 6 electron domains for trigonal bipyramidal and octahedral geometries? When I learned about valence bond theory 25 years ago, chemists thought that d orbitals could combine with s and p orbitals to form hybrid orbitals such as sp3d for the trigonal bipyramidal geometry and sp3d2 for the octahedral geometry. New information has shown the d orbitals are much higher in energy than the s and p orbitals in the same major energy levels, making this energetically unfavorable. Unfortunately, valence bond theory does not offer an easy explanation for bonding in molecules with expanded valences. So we'll limit our discussion of valence bond theory to the sp, sp2, and sp3 hybrid orbitals for the purpose of this course. We've made it to the parting thoughts of the authors for the second lecture covering section 11.3 from the textbook.